To continue in this video, I would like to follow up on the previous discussion that we had on Mohr circle. We considered 2D and we constructed the Mohr circle using equations as well as the graphical approach to build the Mohr circle for a 2D case, plane stress, so-called plane stress case, and then we concluded some important points related to what we discussed before. And this is what we got out of that example. Now, I would like to give you some follow-up for special cases. These special cases are important in terms of the maximum shear stress when a Mohr circle or stress transformation is involved. It is very important because these special cases will give more or shear stress larger than a plane stress, and we should be aware of that. Okay, so if you recall, we had the our 2D that we had sigma 1, sigma 2 principal stresses that we discussed. One thing, notice here that this sigma 1 and sigma 2 have the opposite sign. So if you like, the product is always negative. That is why, because the Mohr circle will include the origin. There might be a case that, and I will go through an example to show you that, there might be cases that if you consider maybe I make it a little bit smaller, okay? If you consider this, so this is sigma 1, this is sigma 2, and for these two cases, the sign of the product of these two is positive. In other words, both of them are positive. Or could be that the Mohr circle sits on the negative side of sigma. Remember, this is our sigma axis and tau axis. For a given set of initial state, this could be sigma 1 and sigma 2. Actually, this will not be sigma 1. Sigma 1 will be the origin. But so let me save this sigma 1, sigma 2 for now. But these are my principal stresses. Now, in this case, both of them are negative. So the product is positive. So if, let me change the pen colors. If sigma 1, sigma 2 is positive, we have more work to do to get tau max, maximum shear stress. And these are called special cases. These are called special cases, as you see here. So this is the special case. If you recall, in the previous case, when you have your circle include the origin, sigma 1, sigma 2 is negative. It's a negative number, or these two have opposite sign. But if they have the same sign, whether positive or negative, then the product is positive. Then you have that is a signal that you have to do more work to get the tau max. Now, I explain it here, but I will go through building an example to show you. If you recall that if I take this cube here, this cube shape, we had a plane stress, so the green same surface is the surface that we say that we have sigma x on it, sigma y say on it, on this side, and let's say on this side we have also sigma y. I will not write the things, we have discussed these things. And this is tau xy, right? And then we go and build our Mohr circle, whether it sits on the left or right or not in any case. But if it sits on left or right of the tau axis, then this is what we are going through now. The thing that we usually don't consider is that in the z-axis, sigma z is 0. So in other words, this Mohr circle will sit in xy plane. This Mohr circle will sit in xy plane. We are talking about xy plane as we discussed before, right? Which is the green one. This is my xy plane, 2D. But here, when we have these special cases, there is a very special point that we need to bring into calculation, and that is the 0, because this is sigma z equal to 0 in the direction of z-axis. Now, once I recognize that, then I can draw another circle with sigma 1 and sigma, or maybe I actually draw that circle more neatly. It's hard to. This is good enough. So the red circle is actually the circle that goes through sigma 1 and sigma 3, shall we say. There's a convention here, and that is usually we consider this order for naming them sigma 1, sigma 2, sigma 3. Sigma 1 should be larger than sigma 2, larger than sigma 3. So in this case, our sigma 3 is 0, and then we draw this circle in the xz plane. So this red one is actually xz plane. Now, if you want to follow this convention, then this will be sigma 3, sigma 1 actually, because it is 0. This will be sigma 2, and this will be sigma 3, because they should be, I mean, usually this is a convention, not a must-have, but this is everybody kind of following. So the point that I would like to emphasize here is that once you have your Mohr circle on one side of the tau axis, you have to pay attention to the special cases. And similarly here, I can draw a circle between sigma 3 and sigma 1. Now, why this is important? Because if I come here for the black circle in 2D, I come here, and this would be my tau max, right? But actually in the red one, if I change my pen color, in the red one, the center would be somewhere here, and this would be my tau max absolute. We call it absolute tau max. And obviously this length is larger than this. So if you design for the tau max based on 2D, obviously you are missing another part of the stress that might happen in different plane, of course, in a XZ plane, but the magnitude is larger. So your material may fail because you are designing for this much shear, but actually this much shear may happen in the medium. So that's the background. That's the special case. Somehow we call it 3D. I mean, kind of, I would say, quote unquote 3D. It is 3D, but not fully 3D because the sigma z is 0 here, and I will discuss following after this example uh, for a fully treatment of stress transformation with the 3D and calculating all of the principal stresses and maximum shear stresses. Okay. Okay, I might as well continue with actually constructing this example. So in this example, we have 150 sigma x and 50 clockwise shear stress. And for the sigma y, I have 40 and obviously minus 50 for the shear stress. So this would be my 2 points. I connect them as we discussed in the previous example. And then I have to find the intersect between this diameter of the Mohr circle and sigma axis, because the center will sit on the sigma axis with the coordinates of 95, and then I come and draw my Mohr circle. So as you see here, these are my coordinates. This is my tau axis. This is my sigma axis. And then my Mohr circle is sitting on the right hand side, meaning that both of if I find my normal stresses, at least 2 of them, always we have 3 bits, but one of them is 0. So if I come here and get the intersect of my circle and sigma axis, the point shown here by letter E and D, these are my normal stresses, 169 and a change. The point here is that this is positive and this is positive. So I have a special case because the product of my 2 normal stresses is positive, a number with a positive sign. So quickly you will see that I will not find it, but if I want to find the shear stress here, I would draw a line parallel to my tau axis and find the intersect of that line with the circle. That is the location or the orientation actually that my shear will be maximum, but not in this case. What I have to do is actually draw a circle between point E and the origin, because this origin is the one that I was discussing here. I don't need this. Is the one that I was discussing here. And I have to consider that because that will give me a bigger shear stress. So I come here and find the midpoint between E and the origin. Midpoint between E and the origin. And then that would be G. Now I draw a circle with center at G and either E or F. Let me maybe change this color to be compatible with what we discussed. So let's make it red. So now I come and find my maximum shear stress based on the red circle, which is in the XZ plane, because this is my X, sigma 1, this is my sigma z. Now, if I want to do that, I have to draw a line parallel to my tau axis from point G and find the intersect of that line with the red circle and this line. Now, this is my absolute tau max. This is my tau max. Okay, so I show the value. So maybe I change the color also to red and maybe give it a, I don't know, a diamond, or also, yeah, a bigger size. Whereas if you wanted to find the in 2D, this would be my, maybe I draw it here. Let me quickly draw it so you have a comparison clearly mentioned here. So if I want to draw a line from here parallel to my tau axis and find the intersect with the black circle, because that's the 2D case. And this K is my, we bring it here. And as you see here, let's zoom here. You see here I have 74, but here I have 84. But the normal stress is also different. But the main issue here is that if you design for 74 and a change, whatever is the unit, let's say megapascal, for example, for shear, there is a orientation in that medium, of course, in the XZ plane, that will exhibit or will experience a higher shear stress, almost close to 10 plus 10 times or megapascal for something. And that's not small. So whether, even if it is this small, that's not the maximum shear, right? So we have to consider that. And then you can take it. And this is this will give you a maximum shear, and the normal stress is, of course, this is 0, doesn't matter. So normal stress is in the XY plane, but this is in the XZ plane in terms of the shear. 45 degrees from the sigma 2 plane that contains sigma 2. Okay, so that is the special case for that's the special case for Mohr circle. And having said that, we can say that we have confirmed the, maybe one more point I mentioned here, and then I close the video. Here, you will realize that you may ask that, how about the circle that from sigma 2, which is here, and F? Yes, you can do that, but that doesn't help us in design, because it doesn't matter. So if I want to do that, actually, for just demonstration purposes, sometimes, as I said, takes scroll up and down to get these tools here. So let me draw it. So we draw a circle between sigma 1 and sigma 0, sigma z. So that's XZ plane. But you could say, how about the Y plane and Z plane, in the YZ plane? So this is the circle. So if I zoom in here, it means that actually Mohr circle method contains 3 circles. The first one, the 2D, the second one, the XZ plane and YZ plane. And if you go back to the original 2D, that we said that when sigma 1 and sigma 2 have different signs, you don't care about this. That is why because there is a circle between the origin and sigma 1, and there is a circle between origin and sigma 2. But both of those circles give you a smaller tau max in this scenario, in this case. Whereas if your normal stresses have the same sign, whether positive or negative, then you have to go through this extra work to find the tau max. Now, this guy here, I don't know, maybe I make it green, gives you a maximum shear which is very small, than much smaller than the maximum shear that you have here, right? Maybe I make it red as well here, so we know that what we are talking about. Okay, so that should do this for Mohr circle, and I close this video. In the next video, I will be treating stress transformation fully from an analytical, using an analytical method fully, and because 3D in three-dimensional, especially when you have usually our stresses are symmetric, but if we don't have symmetric stress tensor, then the whole Mohr circle becomes more tedious and loses its merits based on my understanding. And the beauty of Mohr circle is it is quick. It gives you the principal and maximum shear quickly, and it is very good for 2D. But when it gets to 3D and more complication, the analytical method, as we will be discussing, is much better. Okay, thank you.